In this video, we're going to learn how to solve energy problems when objects are rotating. Let's start by reviewing a simple energy problem. Let's take the example of a block sliding down a ramp. Let's make it a frictionless ramp, and let's say that air resistance is negligible just to make our lives easy. We'll take the ramp's height to be 5 meters, and the goal is to find the speed at the end of the ramp. Now, the steps in order to solve this problem, if you'll recall, include, or at least we start with, identifying all the energies that are present at 2 key times. Our key times will be at the beginning and at the end of the ramp, since we know the most information at the beginning and we want the information at the end. So we want to identify those energies. There are no springs, so we're going to say, hey, there could be gravitational energy, U subscript G, and kinetic energy at both times. At the very beginning, at the top of the ramp, we see that it has a height, therefore it has a gravitational energy, but it starts from rest, therefore there is no kinetic energy. At the bottom of the ramp, it's moving, but its height is 0, therefore it has kinetic, but no gravitational energy. Our next step is to identify if there's any energies that are lost or gained during the process of moving down the ramp. We can do this by identifying a system. We will probably identify our system as the block and the earth. That means that the 2 types of energies within our system are basically gravitational energy and kinetic energy. Since there are no net external forces doing work on the block as it slides down, that means there's no energy gained or lost from the system. That means all the energy stays within the system and the total energy is conserved. Now that I know this, I can use the conservation of energy concept to make a customized equation. If you'll recall, the conservation of energies equation or concept is that we take the total energies before an event, and that will equal all the total energies after the event if energy is conserved. In this case, since energy is conserved, that means that the gravitational energy before will equal the kinetic energy afterwards. From here I can do some substitutions and just simplify by putting in what the equation for gravitational energy and kinetic energy is, and I get mgh equals 1/2 mv squared. Because there's a mass in each term and those masses are the same, that means that I can cancel out the masses on both sides. This means that the answer is independent of mass. I could have an elephant sliding down or a feather and I would still get the same speed at the end. Now it's just a case of some simple algebra to get the final answer of 10 meters per second. Now let's look at this exact same problem, but instead of having a block sliding down the ramp, let's have a ball rolling down the ramp. So in addition to translating down the ramp, it is also now rotating. The question is the answer the exact same as before? Does the fact that we have a solid sphere rolling down the ramp, does it affect the energies present at either the beginning or the end? We want to take a look at this. To see if the rotation has any effect on the energies, let's examine a more simplistic situation where an object is only rotating. Let's take our classic example of Lazy Susan so that we can look at just rotation and a situation with rotation only and no translation. In order to get the Lazy Susan to rotate, I need to apply a force or a torque on the edge of the Lazy Susan. So I might do this by placing my hand, and this would technically be the force of friction, since my hand would be rubbing against the wood of the Lazy Susan, thus giving it this force that is perpendicular to the radius arm. Now, because the Lazy Susan doesn't slide, that means that there must be something preventing it from actually moving in this direction. We know that the Lazy Susan has something that grips the table, and therefore there is a force of friction which is found at the center of mass of the object that is pushing the other way. Thus we can see that the Lazy Susan is in translational equilibrium, but not rotational, since this force does no torque since it's at the center of rotation, but this force being at the edge will torque the Lazy Susan. Will either of these forces do any work? Well, since it doesn't translate this way at all, we can say that, hey, this force is not doing any work. We know work is force times displacement. However, this force the object is translating at this point along an arced path of s. And we can see, hey, since this force is being applied for a distance of s, it is indeed doing work. However, this work is not going into kinetic energy as we normally think about it, because there is no linear velocity that the Lazy Susan has. Therefore, this energy must be turning into a form of kinetic energy that is not translational, but rotational. Therefore, objects can have kinetic energy if it's translating with a linear velocity, or can have kinetic energy if it's rotating with an angular velocity. We know that for translational kinetic energy, we can find that by saying 1/2 mv squared. In the past, whenever we want to find the rotational version of an equation, we just replace all the regular letters with the corresponding rotational letters. And so if we tried that here, we might say maybe the rotational version of kinetic energy would be equal to 1/2 I omega squared. I would like to see if this is true. This has been the general pattern thus far, but I would like to prove it, just so that we can see for sure, or to see if we need to make any modifications. So to do this, what we're going to do is we're going to take this equation that we're guessing is true, and we're going to just modify it slightly and see if we can turn it into this equation, which we know to be true. So I'm going to take this I, the moment of inertia, and I'm going to replace it with the equation that will allow me to turn a moment of inertia into regular translational inertia or mass, and I'm going to do the same thing with angular velocity. So I'm going to replace angular velocity omega with v over r, and I'm going to replace I, the moment of inertia, with m times r squared. Now you'll notice I factored the squared through to both the v and the r on top, and when I do this, that leaves me with an r squared on top and a r squared on bottom, and I can actually cancel these two out, and I get kinetic energy is equal to 1/2 mv squared. Now you can see that this equation here is identical here, and so we say I can turn this equation into something true by following basic algebra principles. Therefore, this equation comes from a true equation and is also true. Thus, we have the final equation, which will appear on your AP equation sheet, that kinetic energy also equals 1/2 I omega squared, where we use this version when we're doing rotational motion, and we use this version when we're doing translational motion. With our new understanding that rotational motion does have kinetic energy, we are now ready to solve this problem. We're going to follow the same steps as we do with regular energy problems, and then we'll see what things change. So, if a ball is rolling down this ramp, first thing we're going to do is we're going to identify the energies present. We still have energies at the beginning and the end, but now we're going to add to that list a possible kinetic due to rotation. Now at the beginning it's still not moving or rotating, so it's still zero, but at the end it's both translationally moving and rotationally moving. So it should have some of each. I'm not sure how much of each, I just want the total here to add up to the amount of gravitational energy I had at the beginning. Now next we still want to see if there's energy lost or gained, so we're going to do the same thing, but this time again we have energy is conserved, but we can know that because there's no net external forces causing a change in energies, but also we know there's no losses or additions to rotational kinetic energy because there is no net torque. That's how we tell if kinetic energy, rotational kinetic energy, is conserved or not. Then we're going to still make our equations. Total energies before equals total energies afterwards, but it looks slightly different. We now have gravitational energy in the beginning equaling both translational kinetic and rotational kinetic at the end. This then equals mgh, this becomes mgh, which equals 1/2 mv squared plus 1/2 I omega squared. Now, an important note is that you can't really solve this equation with both rotational and linear velocities inside the same equation. So you've either got to turn them all into angular or all into linear, and the best thing to do is usually turn it all into linear. So I'm going to substitute I with the equation for I, which, note, is not just m times r squared. This is a solid rolling sphere. That means that we have to use the rotational inertia for a sphere, and this becomes 2/5 mr squared. I replace omega with v over r, and then I can start solving from here. Now, I want to show you something. As I distribute the squared through, I am, again, just like we did in our derivation, able to cancel out this r squared on the top and this r squared on the bottom, and they do cancel out. However, with just rearranging this, it now looks something like this. So now I have gravitational energy equals translational kinetic energy, 1/2 mv squared, plus, and look at this, this just looks like translational kinetic energy. I've turned this rotational energy, 1/2 I omega squared, into linear versions, and it just becomes 1/2 mv squared like before. So what's really the difference? The difference all comes down to this 2/5. This 2/5 came from the rotational inertia of a solid sphere. And because of this, that tells us that, hey, the energy isn't split evenly between translational kinetic and rotational kinetic. But because of this 2/5 coefficient here, that means that only a portion, a smaller portion, goes into rotational kinetic energy, and more of it will actually still end up in translational kinetic energy. Now, that 2/5 might change depending on the shape of the object that's rolling. Let's continue to solve. If I simplify and get some common denominators, I can then add things up, multiply both sides by 10. Oh, and don't forget to cancel out our masses, which is nice. That means even with rotational and translational motion, as long as there's a mass in every term, things will still cancel out and work out just fine, and the mass does not matter, but the shape, notice, still does. Isn't that interesting? All right, so then I can just do my algebra, plug, chug, solve, and I get a final answer of 8.5 meters per second, which is smaller than I was before, which is around 10. So we look at this and we say, oh, why is that? Well, again, that's because rotational energy, some of the kinetic energy was caught up in revolving this thing instead of just moving it physically forward. And therefore, things that roll are slower than things that slide. Now, what if we did this exact same problem again, but this time we just changed the shape? So the total mass is the same, not that it matters anyways, because it cancels out. And we have here, or everything is basically the same. The only difference is that now we have a thin hoop instead. What would change? Well, the whole process would be the same. I still have gravitational to start with, and kinetic and translational kinetic and rotational kinetic in the end. The only difference is what I plug in for I. Okay, so what I plug in for I now changes. Instead of being 2/5, I'm going to use the one for a thin hoop, which, if you recall, is just mr squared. Therefore, I don't have this 2/5 term, and that goes away. And now when I take a look at all this, that means that I have 1/2 mv squared and 1/2 mv squared, and therefore these two are now equal, the rotational and the kinetic energy. That means I'm having more of that kinetic energy caught up in rotating this sphere or this hoop, because hoops are harder to spin since they have a higher rotational inertia than spheres. So as a result, then all the math changes and I get a slightly smaller speed at the end. So if we had a race between a solid sphere and a thin hoop, and they were the exact same masses, you would actually have the sphere get down faster, because the sphere is easier to roll since its rotation, or its moment of inertia, is smaller. Now it's your turn to try. head to WebAssign and try these problems for yourselves to see how to solve problems with energy and rotation.